half scientific.
Excuse me, I'm so sorry.
Oh, no problem. I'll just restate for the recording that my name is Dr. Jessica Noviello, and I'm a NASA postdoctoral management program fellow at NASA Goddard Space Flight Center. My job is very interesting because it's half scientific research and half NASA management. So I get to see both sides of doing science, from the administration side and from the actual nitty-gritty work done on a daily basis by hundreds and hundreds of people. So my research background is mostly on what I would consider ocean worlds and icy satellites. So that just means anything that has an ocean or had an ocean in its past, Earth included, but also moons like Europa and Enceladus, even a little bit of Titan, and as far out as the Kuiper Belt. So all of these different places where ocean worlds could be. And it turns out we discover more ocean worlds. It feels like we discover more ocean worlds every day, especially with the advent of things like the JWST discovering so many more exoplanets, or what will discover more exoplanets for us. But I also have some research background in asteroids and small bodies, which include things like comets and meteorites. I've done work on Venus. I feel like I've kind of worked everywhere in the solar system a little bit, but my expertise is mostly in ocean worlds, icy satellites, and exoplanets.
Wonderful. That's fabulous. And so it feels so exotic compared to what we all get to do every day, I guess. So let me go ahead and let you know that we didn't get any submissions of questions through the web form. So I think the best thing to do at this point would be to open to the audience and see if anybody has any questions, either follow-up questions based on the previous event that we had back in June, or new questions about what Dr. Noviello was just talking about, her research, her work at NASA, and of course, those beautiful photos that we are so excited about. This is your chance to talk to a NASA scientist. Feel free to use the chat button, which is at the bottom of your screen, little like a little speech bubble, or there's also a Q&A icon at the bottom of the screens. Actually, mine, yeah, I'm seeing the Q&A is like the fourth icon from the left.
I do see a question in the chat from Marion.
Okay.
Who asks, will the JWST help you with my research? And the answer is yes, it will. And it will help so many people with their research too. So I'm sure that many of you have seen some of the pictures. I looked at them, and I mean, they're beautiful pictures. But what really blows my mind is seeing the side-by-sides from the Hubble telescope, which has been operating in space for 3 decades now, and side by side with the new images of the same areas with JWST, and the clarity of the images and the amount of detail that we can see, it's really just mind-blowing. Yes, exactly, Marion. It really is just wow. And it's every single person has had that same reaction, whether you are somebody who has studied space for 50 years, or you're somebody who was just scrolling through Twitter one day. Every single person has had the same reaction of just pausing for a moment to take in the images and all that they represent.
I'm going to put one up if that's okay with you.
Oh my gosh, please do. Oh, this is the one. I have so many astronomer friends on Facebook and social media. And so the picture at the left is Hubble, and then the picture at the right is the JWST images. I think that's correct.
Anyway, I think you've got it flipped, or I'm not sure what you guys are seeing, but the one that's more vibrant is the Webb.
Oh, wait, okay.
Right?
This is, I think these are both Webb, but I think they're in 2 different wavelengths. Okay. Sorry. Okay. Yeah, this is what I'm looking at. But I'm going to call your attention actually to the one on the right, the one that's more blue, that has the red center. And if you look dead center in this picture, you can actually see that there are 2 stars. Mm-hmm. And In the Hubble images and even in the image at the left in the different wavelength, you can't see that there are two different stars. So I had astronomer friends who posted the picture on the right, and their comments were, nobody knew that this was a binary star system because we weren't able to see it. The stars were that close together and they're so far away that we could not resolve them with the technology that we had until this week. Just
It's almost like putting on a pair of eyeglasses for the first time.
Yes. And as somebody who wears eyeglasses, yes, that's exactly what it is. It's like, wow, I forgot the world could look so clear. And that's exactly what we're looking at here, except we're not just looking at one world, we're looking at potentially millions of different worlds.
Wow. All right, I'll stop my share.
Oh, it's so pretty. Thank you for putting that up.
Sure.
So it is going to help with my research just in terms of what we can see. So my research, a lot of it is exoplanet detection. And one of the, I believe it was Jane Rigby, actually, one of the scientists who who was part of the NASA live stream, actually talked about indirect versus direct observations of exoplanets. And there are many different ways that we can look for exoplanets, and they each tell us different pieces of information. And one of the things that JWST is going to help us out with is getting very clear spectroscopy of these exoplanets. And we typically get the spectroscopy when there is a light source like the star behind the planet, and then the planet goes in front of the star, and some of that light passes from the star through the planet's atmosphere and then all the way back to JWST or to us here on Earth, depending on how we're looking at it. And then it continues around until it makes another transit. These transits can happen. We're very good at detecting the planets that are close to their star because they tend to loop a lot faster. Something that's closer just can go around more times in the same amount of time. That's geometry. So I actually spaced on what the word was for a moment. So so we have been very good at detecting planets that are very close to their stars. And these are typically very hot planets. They're usually very big planets. So this kind of detection method is very good for finding hot Jupiters. Those are the planets that are the size of the Jupiter that we know in our solar system, but they're much, much closer to their stars. What JWST is going to do is open up the size range of planets that we can detect with that. So we should be able to see down to something like an Earth-sized planet, I believe. So we're not just going to be finding hot Jupiters, we're going to be finding, I guess, hot Earths. Is that maybe like a Venus? I think, what is a hot Earth? I guess that's a Venus. So yeah, we should be finding some exo-Venuses out there. And not only that, but we'll be able to look at the light that's coming from these planets that has traveled from the star through the atmosphere and onto us. And we'll be able to detect what kinds of compounds and chemicals are in these atmospheres. And I think one of the images that we saw on Tuesday was of a planetary spectrum, and that's the one with the squiggly lines, and so there are some peaks and there are some lots of noise at the bottom. The peaks are what we look for, and sometimes the peaks are very pronounced and sometimes they're not, and they're hard to see. And at that point we're like, maybe if you squint, there's a peak there, but it's hard to tell sometimes. So I'm sorry, I think that was a very long-winded answer to your question, Marian, but yes, it's going to help us immensely. I think we're going to find many, many, many thousands more exoplanets than we have with the tools that we have been using up until now. And it hasn't just been Hubble, it's been many different telescopes.
Is this the what you're talking about? I'm not sure.
Yes,
okay.
Yes, that's it.
Wonderful. So this is something that you can look at. I see here, and it's showing you if there's water in the atmosphere or as one of the composing chemicals in the atmosphere of that planet.
So I can break it down a little bit and explain exactly what it is that we're looking at when we see
Yes,
this.
please, much better than me trying to tell
No,
everybody what it is.
no, you did excellent. So this is data that has been cleaned up quite a bit. We do not get it in its raw form looking like this. This has been put through a couple of different data refinement models to, and that doesn't change the data, it just kind of cleans it up a little bit. It's like blowing the, it's like wiping the fingerprints off of a DVD or a CD before you put it in the player. You're just kind of cleaning it up so that you can, or the computer can read the data more fluidly. So what we have here is, like I said before, a lot of little peaks and some detail where we would call that the noise. So it's just a little bit that's underneath the peaks. The peaks are indicative of different types of compounds, and different compounds will have peaks in slightly different places. They might have different numbers of peaks. The tricky part is when you have a lot of different chemicals and they tend to overlap. That makes it very difficult sometimes to say, well, do you have 2 chemicals in this atmosphere, or do you have 3, or do you have 4? In this particular spectrum, so that's just one pattern of squiggly lines. The scientists who worked on this data have been able to pull out what the actual spectrum of water is. And again, this is probably through many different rounds of data cleaning. So if I were to look for something else like carbon dioxide, which is very present in something like an exo, or it's present in our Venus's atmosphere, it's probably very present in something like an exovenus atmosphere as well. I would be looking for peaks in different places. And if I didn't see those peaks, then I couldn't say for sure that there is no carbon dioxide there. I would just be able to say there is no, if there is carbon dioxide there, it is not at a significant level that we can detect with the current technology. So it's very hard to completely disregard something. You can kind of say there is no evidence for it, or there is limited evidence for it, given the limitations of technology. So that's
fascinating.
Yeah, it's a very special way that we have to talk about our science. We can never say like, oh no, there's nothing there, like there's no life on Europa. It's just that we haven't seen any evidence of it. And this is something that I talked about in my talk a couple weeks ago, is just because we haven't found it yet doesn't mean it's not there, but it also doesn't mean that it is there and we haven't found it yet. It's just there's no evidence for it. That is all that we can say.
Okay, that sounds reasonable. Does anybody have a follow-up question or something new that they'd like to talk about? Because I know I have questions, but I don't want to monopolize Dr. Noviello. Marion says, you said there's ice on Mercury. How deep are the craters?
Ooh, that is a great question too. The craters themselves end up being, I mean, they have to be quite deep, because some of these deposits of ice can be up to, I want to say like 135 meters thick. Is that meters or feet? Now I cannot remember. I should really look at my own
It's still pretty
slides.
deep, but either way.
Let me see if I can bring up that slide again from, is this the slide? I have a couple different versions of this one. Oh, yep, here it is. Let me share my slides super quick. Oh, this is fascinating, kind of being the host of this. Wonderful. So here is what we are talking about. So these craters. Oh, okay. So it's 135 feet thick, not meters. Meters would be quite a bit. Oh, Mercury is so interesting for so many reasons. Usually in the solar system, there's something called a depth to diameter ratio. And that's a way of estimating how deep a crater is based on how big it is. We can use these estimates. I mean, it's better if we had a particular laser called a LiDAR to poke down at the surface and actually give us exactly how deep some of these craters are. And Messenger did have that. But for other places that we've visited, we did not have LiDAR. So we've been using these estimates. And typically in the solar system, there's a depth to diameter ratio of about 1 to 10. So say a crater is 100 meters wide, you should estimate it to be about 10 meters deep. That's what that 1 to 10 ratio means. On Mercury, and Mercury is really funny too, because its core is so large. Normally the cores of planets are, I mean, they're big, but they're not 85% of the volume of the planet, and that's what Mercury's core is. So what we think we're looking at when we look at Mercury's surface is not necessarily its crust. We think we're actually looking at like the very top part of its mantle and a very thin crust on top of it. So lots of questions there about, well, what happened to Mercury to make its core so big? Like all of that material that should have been above the core is just gone. So we think maybe there was a giant impact event that kind of stripped it away and left us with the crust. But because the core is so much thicker as well, we also we see slightly different mechanics when it comes to the shape. Well, not so much the shape, but like the size of these craters. And I think the depth to diameter ratio on this, and this is something I should have looked up. I think it's actually deeper than 110. So I think, or 1 to 10. I think if we had something that was, I don't know exactly this number, but I think it's higher than 1 to 10. So the depth of these craters is deeper than we should expect. And part of that is why we can have ice in Mercury. And I'm sorry, I don't have the number off the top of my head. Mercury is one of the few places in the solar system I have not personally studied. But maybe if I can Google that super quick, and I can send out an email to Deborah, and we can send out an email to everybody.
Well, so I think it's really interesting to even think about the possibility that there would be ice on a planet that is so close to the sun. It just boggles the mind. Does Mercury rotate the way Earth does so that it's constantly exposing all of its different surfaces, or does one side always face away from the sun?
Oh, that's a really good question. I think it does rotate. Hang
Because I'm
on.
thinking about like the dark side of the moon. Right?
Yes. So I'm looking up now. Is Mercury tidally locked? Because that's what it means. So when the same side of a planet faces the same way, like our moon always has the same side facing the Earth, we call that tidally locked. And it just kind of means the same thing of like it rotates, so it spins around on its axis at the same rate that it orbits. And so I just Googled, Mercury is not tidally locked. So
Okay.
that is awesome. This is interesting. I'm going to drop this in the chat actually, because I think this is an interesting article. Here we go.
Oh,
Is
fun.
we are all learning new things. Something like, so the moon is tidally locked and it orbits at the same speed that that it rotates, and that's why we always see the same side of it. And a moon like Europa is also tidally locked with Jupiter, so it's orbiting and rotating at the same speed, and that has a lot of weird. That means there are a lot of weird mechanics when it comes to things like heating. Especially in the outer solar system, the main source of heat for moons is something called tidal heating. And it only happens, or it most efficiently happens in a place like Europa, where there is a small-ish or relatively small moon orbiting a very large body at a relatively fast speed. So for scale, Europa is about the size of our moon, but it orbits Jupiter, which is much, much bigger than the Earth is. And it's also a lot closer than Earth and the moon. Europa orbits Jupiter every roughly 3.5 days. So it's quite quick.
Wow.
Yeah. And so it's also spinning at that speed too, because it's always facing the same side. And its orbit is slightly eccentric, which means it's not a perfect circle. It's a very, very slight ellipsoid. But because it's an ellipsoid, however slight, in some parts of its orbit, it's actually closer to Jupiter than at other points. And because it's closer to Jupiter, it's getting a little bit more of that gravitational pull. And as it moves in and out of this slightly increased gravitational pull, the ice shell and presumably the rock underneath the ice shell in the ocean is flexing. It's actually warping a little bit. And all of that motion, especially as it's happening every 3.5 days, all that motion creates a lot of friction, which is translated as heat. So all of that heat is what drives the activity that we see on a place like Europa or somewhere like Io, which is even closer to Jupiter than Europa is. We also see it on places like Enceladus, which is Saturn's moon, and it's the one with the geysers at the South Pole. We see it, or we expect to see it, to a certain extent on something like the Pluto-Charon system. However, Pluto and Charon, they have an interesting dynamic in that they kind of co-orbit each other instead of one orbiting the other. So they're both experiencing this tidal flexing from each other. And part of my research now is to try and figure out exactly how much of that heat is generated in both of these bodies, and how that changes what the planet does with all of that heat.
This is amazing. Like, it just seems like there's so many questions that we still have about our own solar system, and yet now we can see so much beyond it. It's just, there's so much to think about. It's hard to hold it all in my mind at the same time, you know? I mean, I have to say, I've never really been interested in astronomy until like recently. And so now I feel like I'm drinking through a funnel. There's just so much, there's so much to know.
You know, it's so funny that you say, like, yes, we know we're still learning about our solar system. There are so many things that we do not understand. That's why we have so many people working at NASA trying to figure it all out. And what's really interesting is that we talk about exoplanets, and to me, it's pretty obvious. Like, yes, an exoplanet is a planet. It's like the ones we have here in our solar system. But for so long, these exoplanets were nothing more than little specks of light. And it was hard to really think about exactly what they were. And a lot of the people who are working on them are astronomers who are brilliant people, but they're not necessarily trained in things like geology and how to look at these specks of light as planets.
Right.
So we're experiencing not only the shift in thinking because of JWST, but because of the new awakening that exoplanets are planets, and we can talk about them like they're planets, and we can think about them as if they have things like volcanism happening on them, and maybe some of them even have plate tectonics happening on them. Maybe some of them have things like water cycles or methane cycles like what we see on Titan. So we're starting to think of them as not just tiny specks of light, but actual bodies of rock and ice and potentially liquid water too.
So I have sort of an off-topic question, unless someone else wants to jump in, and please do feel free to either type your question in the chat or just I can allow you all to talk as well. Wait, is that okay if I allow
Yeah,
them to
please.
talk? Let's everybody go ahead, and there's only a few people. So everybody please stay on mute unless you do have a question. No need to, there's no pressure, but I just feel like since we are a small group and it's an intimate setting, it's fine, you know, feel free to jump in. I have a completely unrelated question. Does it bother you to watch movies or shows like Star Trek or Star Wars where things are just wrong or implausible or out of date? This is a totally off-topic question.
No, this is a really good question.
If it doesn't, that's fine. If you can suspend disbelief.
It's Star Trek and Star Wars. I feel like they are so different from what I understand that I can separate my science brain from like, oh, this is entertainment. I can enjoy this as entertainment and not try to nitpick it. But there's one movie this is actually something we did in grad school is once a month we would all get to a whole bunch of grad students would get together and we would go down to one of the big conference rooms that, you know, on a Friday afternoon, nobody's using it. So we would just start watching a movie and we would vote on the bad science movie of the month. And then all of us would sit around and just like nitpick everything to do with the movie. And there was one movie, actually, there were multiple movies that we watched. We watched Armageddon, so the one where they have to, you know, they send miners up to blow up an asteroid. The gravity in that movie is totally wrong. Um, the asteroid was really big. I get that, but they were driving around on cars and these gigantic rovers. I'll generously call them a rover, and they were just like bouncing around. And I'm like, if you were going that fast, you would be rocketed off into space, and you would not come back to that asteroid. It's not that big of an asteroid, and it probably wasn't as strong in terms of like its cohesion strength as the movies would have you believe. There was another one that we watched called Europa Report. I really did not like that movie. I'm sorry. Everything was blue tinted. It actually gave me a headache to watch the movie, but that was the one. I should warn everybody. This is a spoiler alert. If you haven't seen it and you would like to, you might want to mute me right now. But it's the one where there's a team of scientists and they go to Europa and they land on Europa, even though Arthur C. Clarke told us not to. And they all get attacked and eaten by this giant squid. I'm not saying that there is no giant squid, although there is no evidence for a giant squid. What really got me on that is like, if there is a giant squid and it was eating people, like people are not a steady food source. What else could it have been eating that it got that big? And why wasn't that animal eating the other things that it should have been eating? Also, the ice shell on Europa is probably not thin enough for a squid to just poke through and like grab people from the surface and bring them down. The ice shell is at least a couple kilometers thick.
Oh my, okay.
So
they got that really wrong.
I mean, it's a movie, right?
Yeah.
And but I remember there were that movie had it was like a found footage kind of movie where they would go to the crew and then they would cut to a politician or a scientist talking about Europa. And there was one thing where somebody said something about Europa and he said something kind of wrong about Europa, and every single person in the movie theater in the theater with me went like, no, that's wrong. That's not true. All of us had the same reaction. It was really fun.
That sounds awesome. Sounds sort of like a Mystery Science Theater 3000 experience.
Exactly.
Yeah.
Those were some good times.
All right, is anybody ready to jump in and ask a question? Because believe me, I can keep going. So I have, oh yes, Miriam has a question.
So I know that tardigrades can live in space, you know, those little microscopic things, and they can also live in water. Are those one of the things you're looking for when you search for life on other planets?
That is a good question. Yes, tardigrades, like water bears, they're one of the few animals that we know can survive in space for long periods of time between the radiation and the lack of oxygen and even the cold temperatures. They're really incredible creatures. If we did, I should say I'm speaking from my personal opinion now. But if we went to a place like Mars or Europa or even Enceladus, and we say that we're looking for life, we would be ecstatic to find something like a tardigrade. I think it is more expected that we find things like tiny bacteria, so even smaller than a tardigrade. We might even find things like fossils, especially on a place like Mars. There are people who there is at least one paleontologist on Mars, at least the Curiosity team, and probably the Perseverance rover as well. Just somebody who specializes in the invertebrate fossils that we have here on Earth. So things like ancient clams and ancient shelled beings. Ah, yes, tardigrades. So we can look for the evidence that there was life there. And that could be fossils, and that could be things like called biosignatures, which is they're chemicals that might come through exoplanet atmospheres that could only be created by a life form, or at least in a certain quantity could only be created by a life form. Those are really hard to find. We're still debating actually exactly what a biosignature is. And when we can call something a definitive signature of life. So it's a complicated question that you asked, is what do we expect to find? And the answer is we have no idea what to expect. Truly, we think we can expect things like microscopic life, and maybe if we're very, very lucky, maybe a tardigrade or something similar to a tardigrade, but we also have to be completely open to anything that might be out there.
Wow, I had no idea. That's so amazing to think about. The media excitement around the images from the Webb telescope is probably like magnitudes of levels less than it would be if they actually found something like that, like a little bacteria out there.
We have to be very, very, very sure that we have
Mhm.
actually found something before we say
Yeah.
anything to anyone. Because
Sure.
can you imagine if NASA said, "Hey, we found life," and then
Right.
the next week we're like, "Oh no, we didn't. Whoops!" Like devastating,
Yeah.
absolutely devastating. So if we say we found life, we are going to have to be incredibly careful about that.
So I have questions actually about like the mechanics of how the data gets shared among the NASA staff,
Mm.
right? So there's the people who are actually working with the telescope itself, like focusing it on things and whatever it is that they do, like mechanically. And then when they get the pictures, like what happens? Do they get put in a central repository and everybody gets to look at whatever they want, or are they divvied up among different divisions? Like, how does that
Mhm.
happen?
So it depends on the mission itself, but it's pretty typical that there is something called an embargo period where I say we, like I'm NASA, the people who are running the mission and getting the data, usually the people who are on these mission teams get to look at the data first. And after something, usually a period of 6 months to a year, once that time period has ended, then those pictures or data or anything, they are released to the general public. And NASA data, because it is taxpayer funded, all NASA data is required to be made public after this embargo period. Of course, you have to know how to use the NASA data repository systems, and you have to know where to look and how to process the data yourself. It usually requires things like special tools. All of the images from past space missions, I know where they are, but they're not always in a usable format. So it's a little bit of an adventure just to try and get to the NASA data. So the answer is the mission teams kind of get first dibs on the data, but the data do get released eventually. Right now, I think now that JWST has finally entered into its science phase, it was either last year or the year before, but at some point there was a call for proposals because you or me as a researcher, if I wanted to look at a particular target with the telescope, I would need to put in a proposal for it, and I would need to compete with other people who want to use the telescope to look at other things as well. So so there's that aspect of it too. Like just because the data are out there, it's not necessarily even what you want. And I think the next year is kind of booked up for time. This is really a system where you have to book years in advance, and you put in a proposal and you hope it gets selected. And if it doesn't, you just keep trying until you get what you need. So I saw Marian asked another question, is Hubble still operational? And the answer is yes, it is. It's not doing great, but it is still operational. I think we were really worried that we wouldn't get the new telescope up before Hubble kind of failed. And at some point we're not going to be able to fix it anymore, and I think that time is coming soon. But it is still up there, still taking pictures. Maybe they won't be as impressive now, but it was an incredible mission. I mean, it was up there for 3 decades, and it's still doing great work. It's not as, flashy as JWST is, but it's still there, and it's still kicking. It's still doing its work, and it changed how we saw the universe, and it changed what we understood about the universe. And I respect the mission for that, and I thank everybody who ever worked on it.
So as someone who's more familiar with the resources that NASA has, if you were to recommend a page or a group of web pages or sites that you think the public probably doesn't know about but would really benefit from knowing about, do you have like a favorite resource that you would point us to?
There's one that I used a lot in my own work, and it helped me find images that I wanted to use, and let me just locate them. It's something called Pilot, and I just put the link in the chat. It's a system that's run by the US Geological Survey, and it takes data. So it's not the actual data repository. This is a user interface that makes it easier to use, and I think it works very well. Different missions have different places in the NASA system where it goes. It's really confusing. I don't fully understand it. But if you want to look for pictures of, of the surfaces of planets, this is the place that I would suggest that you go.
I'm writing it down.
And not all of the images are going to be very helpful or very usable, but at least with this tool, you can explore the different parameters, and you can get a sense for yourself what kinds of images were taken, and of what bodies in the solar system, and in what wavelengths they were used, or the pictures were taken in. Oh, Marion, you are so full of questions. I love it. Marion asked, could there be water on an asteroid? So there can be water locked up in different minerals on an asteroid, but we don't have any evidence of running water on an asteroid. What would happen if there was water on an asteroid is because asteroids don't really have any kind of atmosphere to protect the liquid water, and space is so cold and so dry, the liquid water would evaporate very, very quickly. So we can have something like water on Earth, and there was running water on Mars, and there might have even been liquid water on Venus too. In fact, there's good evidence that there used to be oceans on Venus before it evaporated into the atmosphere. But the reason those planets can have water is because they have atmospheres. How did water get on Europa? That is such an excellent question, and the answer is I have no idea. There are, what probably happened is there was, when the planets and the moons were forming, Europa formed beyond the snow line, which is the limit where water could exist in a solid state, so as ice. And if you got too close to the sun, you would, the ice would evaporate, or the ice would melt and then evaporate. But beyond this snow line, that's where all the ice could exist kind of safely. But what happened is, this is complete speculation. I have not done the research on this, but this is my best guess based on what I know. Europa probably formed like all of the other planets. It formed as a mix of dust and ice and rock. And then as it evolved and it grew the layers of core and mantle, all that process also created a lot of heat. And what I would guess is that that heat was able to melt a large fraction of that ice and form the ocean that we have now. The reason that it is still liquid is because of what we talked about earlier with that tidal flexing, so that that slight change in Europa's shape that just keeps that heat flowing. If that ever stopped, there would be no ocean. So that's what I think happened. Although again, that is pure speculation, and I know other people have worked on this topic. And then if that explains Europa, well, what happened to Io, and what happened with Ganymede, and what happened with Callisto? So that I don't know. And that's the problem with studying planets. It's like you can always explain what happened with one of them, but then you have to explain that same process affecting all of the other satellites too. And that's where it gets really hard, where it's like, how come it worked this way on this body, but it worked the other way on the other body? And like, what is different about the two of them, and why did that happen? So we are still working on it.
So when you say that the tidal flexing produces heat, obviously it produces enough heat to melt the ice. So it's over 0 degrees, but how much heat are we talking about?
That is another good question. Because there are equations that we can use to estimate things called the heat budget of a moon or a planet. And then we can go with satellites and directly measure the heat that's coming off of it. Oh my goodness. I want to say it's something like 1 terawatt of energy. It's something on the order of terawatts. Now I can't remember if it's 1 or if it's like 15 terawatts, but it is a lot of heat coming off of this. I think I've been in exoplanets world for too long. I'm forgetting all these details about Europa. But it is a lot of energy. One of the big problems is that when we are using these models to study the heat budget, sometimes our equations and our estimates are not what the missions say the heat budget is. So it's like, well, that's direct evidence. We know that that is probably right, barring some kind of catastrophic technical failure. So why are our equations not coming up with the same numbers? And this is a big area of research of that, like, what are we missing component to some of these models? I mean, we're still doing a good job, right? But it's like, it's getting that last 10% of the details. That's where 90% of the work is. So I'm sure many of you can relate to that. It's like, it's the devil in the details kind of, and that's true in space as well.
There's a lot of scientific process that you're grappling with on a day-to-day basis. It's not just like framing your question, aiming the telescope, and getting the answer. There's a lot of, it sounds like there's a lot of refining and reiteration. And
yes. Yes, and it's never just one person doing this work. This is why missions are made up of teams of people, because it's impossible for one person to know everything about everything. But you don't have to, because like, I'm an expert in geology, but the person working next to me is the expert in tidal heating. So we can work together to solve a common problem. I don't have to do anything on my own.
Okay, we have another question. Is there any other icy moon? And I don't know.
Oh gosh, there are so many icy moons. I guess the closest one to us, I mean, our moon technically has ice on it, but it's not necessarily an icy moon. There's an asteroid, actually it's a dwarf planet in the asteroid belt called Ceres, and that has a lot of ice on it too. It actually even has what we think is an ice volcano on it, and it's the closest ice volcano to the Earth. Beyond that, we have Europa, which I've talked about. We have other moons like Ganymede, which is the biggest moon in the solar system, and Callisto, which has one of the most cratered surfaces in the solar system. So it's very, very old. And there's Ceres. Oh yeah, so Ceres is the dwarf planet that lives in it's found in the atmosphere. It's found in the asteroid belt. There we go. And I'm trying to see if I can find Ahuna Mons on here. So Ahuna Mons is what that ice volcano is called, if it is an ice volcano. We're pretty sure it is, though. So this is one of these ice-rich places, and actually, we might see in the next 10 to 20 years, we might actually see a Ceres sample return mission. So like send a probe to Ceres and pick up some dirt and bring it back so that we can study it on Earth. So yeah, there's also Enceladus, which is a moon of Saturn. There's Titan, which is another moon of Saturn. There are many of the moons around Uranus, so pretty much all of those. And then I think the coolest one is Triton, actually, which is a moon of Neptune. So Neptune has other moons too, but Triton is the coolest one, so it kind of gets all of the attention. But there are really cool ones around Uranus too, like Miranda and Ariel, Umbriel. And what's really cool is that, again, in the next 10 to 20 years, we're going to see a mission that actually goes out to Uranus and studies these moons and Uranus itself in a lot more detail. This is a prioritized mission now. So after NASA is done with the Europa Clipper mission, which should launch in 2024, fingers crossed, then we'll, once that launches, we'll all turn our attention to Uranus and try to work on that mission. But it's a long way away. So even when we launch it, it's still going to take many years to get there. So we have to be very patient for that. We can talk about it now in 2022, but we might not see new data of the Uranian satellites until 2040. So one of the sad parts about studying space, especially the outer solar system, is we have to wait long periods of time for us to get new data back. So this is why we are so desperately trying to get more missions to the outer solar system, because it takes so long to get out there. And all of the Mars friends that I have, they're like, oh, we have to wait 8 months for our probe to get to Mars. And I'm like, that's nothing. You don't know how lucky you are.
Scientific humor, scientific one-upping.
Yeah.
Oh, wow. This is fascinating. This is so interesting. Who else has a question? Oh, I wanted to know, like, if there was one planet or moon that, or, asteroid belt, I guess, that you could visit, which one would it be? That's, librarians we have to encourage the use of the imagination. So tell us, like, if you would to picture yourself out there in the solar system, where would you want to go?
Okay, I'm gonna maybe scandalize my colleagues right now and say I wouldn't go to Europa, because I know we're going there already. So I would want to go to a place where NASA is not going. And I would say I would want to go to the Pluto-Charon system, actually.
Okay. Can you tell us more about, like, what the appeal is of that one? Like, what is it about that it sparks your imagination?
So I remember watching those images come back for the first time, and it was the first time anybody had seen Pluto up close. And it came onto this giant screen that we had at Arizona State. That's where I went to grad school. And the little heart that we can see, it's just so surprising. And then when we looked closer at that heart-like structure, we discovered glaciers. Again, I say we as in not me personally, but we as in planetary science and all the people who worked on that mission. We found glaciers, and we found signs that Pluto was still active. We expected to go out and say, oh, it's so small and it's so far away, it's probably not doing anything, and it hasn't done anything for billions of years. And that turned out to be completely untrue. And not only that, but we have, and that's when we discovered that it wasn't just Pluto and Charon, but 4 other moons as well. And just kind of mind blowing. It's like, whoa, there was more stuff out there. How did we not know that? Ah, yes. Sharon is super cool too. Are we going to get Pluto back in the family? Oh, this is a big, I'm laughing because this is a really big controversy of not just in the public sphere of like, is Pluto a planet or not, but also in the scientific realm. Last year, I I read a paper that was something like 80 pages long. It was a very long paper, but it was arguing very strenuously that Pluto should be called a planet again. And not only should Pluto be called a planet, but we should call all of the moons planets as well. We already call them planetary bodies. There's a lot of historical precedent for why they should be called planets. You know, why not just call everything a planet? We can say like major planets and minor planets and just refine the terminology altogether. Before I read this paper, I was of the opinion that it does not matter what Pluto is according to our Earth terminology, because it's still really cool. We're going to go out and we're going to study it, and we're going to try and learn all that we can about it. Unfortunately, no, we are not going to go back to Pluto anytime soon. It was just a flyby mission, so we just like zoomed past, and that was kind of it. I would love to see a mission go back. We're going to have to wait a couple decades for that, unfortunately. So, but I would hope that we go back, because once we do go back, we're going to have such better technology, and maybe we'll be able to even land on the surface. Maybe we'll be skilled enough to do that. So, oh gosh, I feel like I hated when they did that. Yes, when they downgraded Pluto. It turns out it was actually kind of a this was a dark moment, actually. So the people who control the names of planets and the features on planets and moons is the International Astronomical Union. And there were a lot of people who were very upset with the IAU and exactly how they took the vote to downgrade Pluto. And that was another component of this 80-page paper that argued that precedent was broken and protocol was not followed. So the vote itself is technically invalid, and we should revisit this. So when I say this is a big controversy, I mean like people are vehemently fighting about it, and lots of hurt feelings on both sides. I'm a little afraid to get into it myself, actually, because it's a lot of anger, actually, but I think like justified anger, because there are people who spent their whole lives trying to get the New Horizons mission to go to Pluto. And that mission took a decade and a half to get proposed and then funded and then built and then launched. And then just a year later to have Pluto downgraded from planet to the dwarf planet status really hurt a lot of people who had spent a lot of time to bring Pluto up to the forefront in the first place. So there's a lot of history there. I will say that it took a long time to make that happen. So how long does it take to get to Pluto from Earth? It took 9 years. It took 9 years to get from Earth to Pluto, and it didn't go in quite a straight line. It had to actually do some loops between Jupiter and Earth to do things called gravity assists. And it's you go close enough to Earth that you pick up a little bit of speed, and then you just kind of like slingshot out, and that helps save fuel to go far. That is really, really, really long. Yes, it is. That's why we have to start planning missions now, because then they launch in 6 years. But it's 15 years until we finally get data back. And you think about like, I'm 30 years old right now, I'll admit that. And if we launched a mission tomorrow to Pluto, I would be 45 by the time I saw pictures from that mission of Pluto. That's a long time to wait.
Yeah. So it means that astronomers and scientists have to plan their careers carefully and have intermittent sort of projects going on to tide them over until they get the big one off the ground and get those answers. This has been wonderful, and I really appreciate your time, and I appreciate our wonderful attendees this evening, Pat and Marion and Noel. We are so grateful to be able to offer these programs to you. I did put a link in the chat about where you can go to find out more about the events at Alexandria Public Library. We will be having another astronomer later this summer. And he specializes, I believe, in black holes and things like that. So different, completely different type of astronomy and studies that he's doing. And I just can't thank you enough, Jessica. It's been wonderful, and we've learned so much, and we have a lot to think about and a lot to take away and share with our friends. So thank you very much, everybody.
Thank you all for coming, and thank you for having me again.
Yes, thank you. Have a good evening, everyone. Bye-bye.
Bye, everyone.